Welcome back, design junkies, to Mechanical Engineering Made Simple. Today we're diving deep, really deep, into a whole stack of material. It covers everything from, basic handbook stuff, tolerances, fits, hardware, right up to the cutting edge, like conceptual modeling and even nano-manufacturing ideas.
Yeah, it's quite the range, a huge amount of technical knowledge. But our mission, really, is to boil all that dense info down into something actionable for you. We're going to focus on what makes or breaks modern design today. The three pillars, if you like.
Which are?
High efficiency, mastering ultra-precision kinematics, and, crucially, sticking to real-world manufacturing standards. You can't ignore the reality of how things get built.
Absolutely. Okay, let's kick things off with that first pillar. Efficiency. It feels like in modern engineering, we're not just aiming for strong anymore, but smart, right?
Exactly. Smart and lean. The big conceptual shift, especially if you look at aerospace or automotive, is all about topology optimization.
Okay, so topology optimization, what's the core goal there? What's the non-negotiable objective?
It sounds simple, almost elegant, really. Maximize the structural performance while, and this is key, minimizing the amount of material you use. Aggressively.
Like nature does, bones or trees, that kind of thing.
Precisely. It's biomimicry in a way. Put material only where the load path actually needs it and nowhere else.
And the payoff. Is it just saving a bit of weight here and there or something bigger?
Oh, it's systemic. Way bigger than just saving a few grams. The immediate benefits are, well, first, significant cost savings. Less material, less cost. Then there's the reduced environmental impact. Less material means less energy to produce it, transport it.
And better performance, too? Lighter usually means faster or more agile?
Enhanced functionality, exactly.
Yeah.
Lightweighting is huge. So yeah, it's driving sustainability and cost-effectiveness in any sector using complex parts.
So how does the software actually find these, perfect shapes? Is it just fancy FEA?
It goes way beyond standard FEA simulation. These conceptual models use pretty advanced optimization techniques, think genetic algorithms, particle swarm optimization, that sort of thing. These let the software explore literally millions of potential material layouts. It finds solutions that, honestly, a human designer might never even think of. They look strange sometimes, but they're structurally ideal.
Minimizes prototyping, too, I imagine.
Big time. Cuts down on costly physical prototypes.
Right. So this sounds incredibly powerful. Why isn't every single company using this for every single part starting tomorrow? What's the holdup?
That's the million-dollar question. The real friction point is standardization, or rather the lack of it.
How so?
Well, think about it. Aerospace has different material needs and failure modes than, say, medical implants or automotive chassis. Each sector has unique requirements, unique materials, unique constraints.
Right.
So integrating these optimized models into existing standardized manufacturing workflows gets really complicated. You often need custom post-processing, extra verification steps. It's not quite plug and play yet.
So the ideal digital model meets the messy reality of the factory floor.
That's it exactly. Bridging that gap is the challenge.
Okay, fascinating. So from macro efficiency, let's pivot hard to the micro world, ultra precision. When you need motion control down at the Angstrom level, we're talking nanotechnology, semiconductor lithography, those traditional sliding joints with friction are just out, right?
Completely out. Friction, backlash, stiction. They're killers at that scale. That's where flexure bearing systems come in. They're the go-to solution.
Because they bend, not slide.
Right. Motion comes from the material elastically deforming, so you get incredibly smooth, fine movement, no friction, no backlash. They are pure kinematic systems in essence.
But getting that Angstrom-level repeatability, that sounds incredibly difficult. You can't just bend any old piece of metal, surely. What's the checklist?
No, you definitely can't. There's some non-negotiable conditions you absolutely have to meet. 4 main ones.
Okay.
First, the material itself needs low hysteresis. You don't want it remembering previous stresses.
Yeah.
That's why you see specialized materials, sometimes even single crystal silicon, in extreme precision apps.
Right. Minimizes internal friction.
Exactly. Second, no dislocation motion in the material's crystal structure. That means your operating stress has to be significantly less than the yield stress. Keep it purely elastic.
So way below yield. Got it.
Third, the load has to be super repeatable. Same magnitude, same direction, every single time. Any variation throws off your position.
Makes sense. And the fourth?
And this one is critical, linking back to manufacturing reality again. Perfect assembly. Any tiny bit of microslip where parts join or any unintended friction introduced when you bolt it all together, boom, your angstrom repeatability is gone. Wasted.
That really drives home how design and manufacturing are inseparable at this level.
Absolutely.
Okay, let's step back for a second. The fundamental framework for all motion is kinematics, constraints. Remind us of the core principle there.
It boils down to a really simple but powerful equation. Degrees of freedom, let's call it R, equals 6 minus the number of constraints, C. So R equals 6, C equals F.
6 being the possible motions in 3D space. Translate XYZ, rotate around XYZ.
Correct. And by applying constraints, you remove freedoms. The goal is usually to get R down to 1 for predictable single-axis motion. And if you want that predictable motion, especially linear motion from rotational constraints, you must follow Blanding's rule of complementary patterns.
Okay, don't just name the rule. What happens if you break it? What's the engineering consequence?
Bad things happen. Blanding's rule basically says that for pure rotation, the constraint lines must all intersect the desired rotation axis, and for pure translation, they must be parallel. If you violate that, say, your constraint lines don't intersect the rotation axis properly, you're not just getting a bit of error, you're introducing over-constraint.
Meaning
Meaning the part has to deform in weird, unpredictable ways just to move at all. You lose predictability, you introduce parasitic motion. For Angstrom-level work, that's fatal. You build chaos into your system.
wow. So from the clean, rigid world of kinematic points and lines, we instantly hit the physics of the material itself, elasticity. How do we bridge that? How do we mathematically ensure our flexure is stiff enough but still compliant enough?
That bridge is compliance, or its inverse, stiffness. We use formulas linking the geometry and the material properties. Take a simple example, a cantilever beam deflection. The deflection, delta, is proportional to the source, F times the length cubed, L cubed, divided by 3 times Young's modulus E times the area moment of inertia, I. So delta SC dot L3, 3.
Okay, I remember that one.
What that formula shouts at you is that precision design is always about 2 things. The material's inherent stiffness, its Young's modulus E, and the shape's rigidity, captured by I, the geometry. You have to engineer both.
Right. Material and shape.
You got it.
Okay, so from the theoretical purity of a flexure, let's jump right into the heart of manufacturing reality. The humble, ubiquitous, bolted joint. We need them stiff, especially preloaded ones. Now here's a classic engineering question, maybe even a trap. When you calculate the equivalent stiffness of that preloaded joint, the bolt stretching, the flange compressing, are those stiffnesses acting in series or in parallel?
Ah, yes, the classic trap. They look like they're in parallel, side by side. But for the stiffness calculation, they act in series.
Why? Explain that.
Because the defining characteristic of elements in series for stiffness is that they share the same force. The preload force is the same in the bolt, causing stretch, and in the flange, causing compression.
But the displacements are different.
Exactly. Same force, different displacements means they combine like springs in series. If you calculate it assuming parallel, your prediction for the joint's dynamic response will be completely wrong.
Okay, series it is. Good clarification. Now, another common bolted joint misconception, shear resistance. If I apply a load sideways, perpendicular to the bolt axis, is the bolt shank taking that shear load?
Usually no, or rather it's designed not to. In a properly preloaded joint, the shear load is almost entirely resisted by the friction between the clamped members.
Friction again.
Yes. The critical factors are the coefficient of friction between the surfaces and, crucially, that preload force, F preload, clamping them together. The bolt's job is primarily to provide that clamp load.
So if you really need positive shear location, relying on friction isn't enough.
Definitely not reliable enough for precision location. For true positive shear resistance, you absolutely need dedicated features like precision dowel pins or shoulder bolts. They physically prevent sliding.
Right. And getting that preload, that clamp force, correct, is vital for the friction to work. But you mentioned measuring stretch directly is often impractical on an assembly line. Strain gauges are expensive. So how do we typically measure preloads in practice?
We usually default to the least precise method, ironically, for one of the most critical parameters. We measure the applied torque on the bolt head or nut.
Torque wrenches.
Torque wrenches, automated drivers, yeah. It's fast, it's cheap, it's easy to implement on a production line. But it's notoriously not ultra-repeatable. Why? Because the actual preload you get for a given torque depends heavily on the friction under the bolt head and in the threads, and that friction varies with surface finish, lubrication, dirt, everything.
So we're accepting a fair bit of uncertainty there.
A huge amount, in many industries. It's a calculated risk, a trade-off between precision, cost, and speed. It works most of the time, but it's far from perfect.
And because of that imperfection, standards become absolutely critical. They're the safety net, defining how parts should fit together, even with these variations.
Exactly right. Standards are the bedrock of reliable assembly. Think about screw threads, unified inch threads, metric threads. They have rigorous classification systems like 1A, 2A, 3A for external inch threads, 1B, 2B, 3B for internal, or 6G, 6 out for common metric fits. These dictate the quality and clearance.
And beyond threads, the fits between shafts and holes.
Same story. Governed by standards, ANSI, ISO, they define tolerance zones and allowances to create different types of fits. You have clearance locational fits for parts that need to assemble easily, transition fits where it might be a slight clearance or slight interference for snug location, and then the interference fits, force fits, shrink fits, where you need significant force or temperature difference to assemble them.
Ensuring parts made anywhere in the world can actually connect as intended.
That's the goal. Predictable interfacing.
Okay, let's wrap up by looking at actually transmitting power and motion. Belts and chains. We often see synchronous belts, like timing belts, compared to traditional V-belts. What's the niche for synchronous belts, and what's their main trade-off, especially noise?
Synchronous belts, you mentioned Power Grip GT3. HTD is another common type. Their big advantage is positive, non-slip engagement. They're for timing applications where you need precise positional control.
Right.
The trade-off is typically noise. That meshing action of the belt teeth engaging the sprocket teeth generates noise, especially as speed and belt width increase.
Is anything being done about that?
Oh yeah, manufacturers are constantly improving tooth profiles.
Right.
The Gates GT3 profile, for instance, was specifically designed for better, quieter meshing compared to older designs like HTD. Using larger sprockets also helps reduce noise.
And since they rely on that precise tooth meshing, alignment must be super critical, right? What happens if things are slightly off?
Oh, misalignment is an absolute killer for synchronous belts. And V-belts too, actually. Even slight angular or parallel misalignment causes high tracking forces on the belt trying to pull it off the sprockets. This leads to edge wear, increased noise, and eventually catastrophic failure of the tensile cords inside the belt.
Are there hard numbers for acceptable misalignment?
There are. For something like a standard V-belt or micro V-belt, the general rule is misalignment shouldn't exceed about 14 of a degree angularly, or maybe 116 of an inch parallel offset per foot of distance between the shafts. Exceed that and you're drastically shortening the belt's life. Guaranteed.
Wow, that's tight. And getting the installation tension right is obviously key too. Why is that initial tension so important?
It does three crucial things. First, it provides the grip needed to transmit the torque without the belt ratcheting or jumping teeth under peak load. Second, it has to compensate for the natural tension decay that occurs as the belt seats itself into the grooves right after installation. You over-tension slightly initially. And third, it helps pre-stress the drive frame and maintain overall system stiffness.
How do you measure it accurately?
Often it's done with simple force deflection methods. Push on the belt span with a known force and measure how much it deflects. Or, for more critical drives where you know the operating torque, Q, you can calculate the required static tension using specific formulas provided by the manufacturer.
Okay, quick switch to roller chains. What are their main jobs, and when does an engineer say, okay, this chain is done?
Roller chains are workhorses. Two main functions, power transmission, obviously, and also conveyance, moving stuff along assembly lines, for example. Standardization like ANSI, ISO, JIS, makes selecting them pretty easy.
And where limits?
They're surprisingly durable, but they do stretch over time as the pins and bushings wear. The rule of thumb is replace a power transmission chain when its length is increased by about 1.5% due to wear. For a conveyor chain, which often runs slower, you might let it go to 2% elongation.
Beyond that, things get inefficient or risk jumping teeth.
Exactly. Reduced efficiency, potential for sprocket damage, and eventual failure.
Is there anything to help with maintenance, specifically lubrication? Chains need oil, right?
Lubrication is absolutely vital for chain life. It reduces wear, dissipates heat, cushions impact. But yes, some applications make frequent lubrication difficult. That's where specialty chains come in. Things like Tsubaki's Lambie Day series or similar products from other brands. They use oil-impregnated, sintered metal bushings around the pins.
So they're self-lubricating.
Effectively, yes, for a period. They offer significantly longer wear life without needing external relubrication, especially at low to medium speeds.
Yeah.
Big maintenance saver. One important note, though, O-ring chains, often used on motorcycles, seem lubrication-free but are usually not great for industrial conveyance.
Why not?
The O-rings seal lubricant in, which is good, but they also add friction and stiffness to each joint. After the chain articulates around a sprocket, it might resist straightening out properly, which is bad for conveyors.
Good distinction. And even with standard chains, lubrication needs aren't constant.
Right. You generally need to lubricate more frequently right after installation as the parts break in.
Yeah.
And definitely more often under harsh conditions, high speed, heavy loads, high temperatures, dirty environments.
Yeah.
Tailor the schedule to the conditions.
Okay, we have covered a massive amount of ground today. It's really clear how these different areas have to mesh, doesn't it? From, the high-level computational optimization, trying to sculpt the perfect lightweight part, down to the Angstrom-level precision needed for flexures,
Right.
and then grounding it all in the reality of bolted joints, tolerances, and making sure belts and chains actually deliver the power reliably.
It really does highlight that constant interplay, doesn't it,
Mm-hmm.
between the conceptual ideal and the, let's say, practical realities of manufacturing and assembly. And thinking back to where we started, with topology optimization aiming for that perfect, mathematically ideal shape and material density,
Mm-hmm.
it brings up a really interesting final thought for you to consider. Given that topology optimization generates these, well, often complex and theoretically perfect forms, how does that conceptual design process need to evolve? How can it start to proactively model and actually account for the real-world limitations we just spent time discussing?
You mean things like...
Things like the inevitable microslip in assemblies, the practical alignment tolerances you can hold on a factory, the material hysteresis that limits flexure precision, the uncertainty in bolt preload from using torque.
So building the imperfections into the optimization loop from the start.
Exactly. How do we bridge that gap, not just in post-processing, but right from the initial design concept?
Yeah.
Because closing that gap between the perfect simulation and the imperfect real-world manufactured part, that feels like where a lot of the next big engineering innovations are going to happen.
A fascinating challenge indeed. Building the real world into the digital twin more effectively. To my fellow design junkies, I want to say thank you. The show exists because of you. The ones who chase precision, who think in torque curves and tolerances instead of trends. If you enjoy the show, please let us know with a like and a comment.